Hi, hello. Hello everyone. Okay, this video I'm going to show you some mechanical property calculation example. Okay, so this example is also reference from the textbook. Okay, it involves some mechanical property calculation of material. Okay, so here we see, let's start with the problem description. Here he said a solid circular rod that is 600 millimeter long and 200 millimeter in diameter. Okay, and it's subject to external loading. Okay, and subject to axial force P 50 kilonewton. And he said the elongation or the deformation is 1.4 millimeter. Okay, and also and when we apply the external loading on this body, it has the diameter contract, and the diameter contract from 20 millimeter to 19.9837 millimeter. You say, okay, we have this information. Okay, can we use this information to determine the modulus of elasticity and modulus of rigidity? Yeah, but the modulus of rigidity, in my opinion, it's better to call it shear modulus. So that's, to me, this problem is using this problem description, okay, to determine the elastic modulus and shear modulus of the material. And we assume the material does not yield. Okay, that's very important because this assumption is the material, when we apply this external loading, the material is under the elastic region. Okay, because if material is yield, I think we cannot do any calculation because it's in plastic region. I think that right now there's not a good formula, a good theory for plastic region. So it may depend on experimental measurement. Okay. So what's the so let's start with it. You want to us calculate the E and G. Okay, E and G. Wow, let's do math here. You want us determine the E and G. Okay, in elastic modulus, and the shear modulus. So we want us determine the E and the G. Okay, and let's look at this. So let's go to Hooke's law. The Hooke's law said the axial stress, normal stress equal to elastic modulus times the shear strain, and the shear stress equal to the shear modulus times the shear strain gamma. So in this problem, as we see, what information this problem give us? Okay, he give us external loading, 50 kilonewton. He said elongation is 1.4 millimeter. Okay, so I think this give you some information. So it give an axial force. So we know the normal stress is equal to the normal force divided by area. Okay, and it's give you the initial diameter, right? Initial diameter 20 millimeters. So this give you the shear stress. This give you the shear stress. I'm sorry, normal stress. Okay. And the normal strain, okay, can we have normal strain? Yeah, we have normal strain here. Normal strain, he give the deformation under this axial loading is 1.40 millimeter, and we have the length before the external loading. Okay, it is 600 millimeter. So you know what's the strain? Strain is the deformation divided by L0. Okay, so that's L minus L0. Okay, divided by L0. That's the normal strain. Okay, so in this, for this problem description, we can have the normal strain and normal stress. So based on this information, we can obtain the elastic modulus. That's no problem. But what about the shear modulus? Shear modulus, okay, in this problem we don't have anything. This problem didn't give us anything about the shear strain or shear stress. Yeah, I cannot see that. Okay, I don't see anything related to shear strain and shear stress. Okay, so and how to calculate the shear? How to calculate the shear modulus in this problem? So I think there's another relation between the elastic modulus and shear modulus. That is, I think it's G. Sorry. I think there's a more is G is equal to E divided by 2. Eh? Let me see. Mhm. Okay. Okay, let me see my notes. Okay, 2 times E 1 plus the 1 plus Poisson ratio. Okay. So, and this relation connect to the shear modulus and elastic modulus, okay, and they are connected by the Poisson ratio. And what is the Poisson ratio? Do you still remember the Poisson ratio? Poisson ratio is there's a negative sign is the strain in the longitudinal direction divided by the strain in the lateral direction. Okay, longitudinal direction, strain in the longitudinal direction divided by the strain in the lateral direction, right? Let me see. Lateral longitudinal. Okay, let me see. Or did I write it in reverse? Let me see. Let me check the formula. I really kind of forgot. Okay, what's the shear? What's the Poisson ratio? Oh, it's lateral divided by longitudinal. Sorry. Yeah, I got it reverse. Yeah, so be careful. Yeah, my memory is not that good. Okay, so it's lateral direction divided by longitudinal longitudinal direction. Okay, so okay, I think that's the correct formula for the Poisson ratio. Okay, okay, okay. So, and in this problem, can we find the Poisson ratio from the problem description? Yeah, we can have because we have he give us deformation on the longitudinal direction. And also, he give us the diameter contract from 20 millimeter to 19.9837 millimeter. Okay, that you can use this information to determine the lateral strain. Okay, lateral strain. Okay, so lateral strain. Okay, so do I need to draw the picture of this? Okay. Yeah, but it's very small. Okay, it's not meaningless to draw a picture. Okay, so let's start with the calculation. So first of all, we can find the E. Okay, find elastic modulus. Okay, so we have the shear normal stress. Okay, normal stress is equal to the normal force divided by area. And what's our normal force? 50 kilonewtons. So it's 50 times 10 to the power 3. And what's our area, cross-section area of the cross-section, or area cross-section? So it's 20 millimeter in diameter, so it will be pi over 4, 20 times 10 to the power minus 3 square. Okay, so what's the okay, what's the value? Okay, I didn't calculate value. Okay, I didn't have the value on my notes, so maybe I calculate myself. So what's the, okay, 50, let me, 50 times 4, times 50 times 4, divide 3.14. Okay, divided 200, divided by 200. So it's 0.159. 0.159 and times 10 to the power minus 6 or 10 to the power 9. Wow, that's very huge value. So what's the, so it's 159 times 10 to the power 6 par. Okay, so it's megapar, 159 megapar. I hope my value is right. My calculation is right. Okay, so what's this normal strain? Okay, he said that deformation is elongation is 1.4 millimeter and the original length is 600 millimeters. So actually, the normal strain, okay, right here, normal strain is equal to 1.4 divided by 600. Okay, so in the last time I say it's better to have 3-digit, no, 5-digit. Okay, so 0.000002 is 33, right? 1, 2, 1, 2, 3. Okay, so that's our strength. So our modulus is just what's our modular? Modulus is equal to divided by this value. Oh, it's so huge. Did I calculate it right? Okay, so let's see. Okay, so 159 times 10 to the power 6, and our strength is 2.333 times 10 to the power minus 3. Okay, so 159 divided 2.333. Okay, so it's about 68.15. So it's 10 to the power 9. Okay, pa. Okay, so it's about the 68.15 gigapa. Okay, is correct. Okay, looks like right. Okay, looks like right. Okay, so it's gigapa. Okay, 68.15 gigapa. Okay, it's giga. Okay, and don't forget giga is 10 to the power 9. Okay, and then we have to determine the shear modulus. And shear modulus, we need the Poisson ratio. And Poisson ratio is a deformation in lateral direction divided by longitudinal direction. And we already have the normal strain. Normal strain here. We have normal strain. Okay, so this is a LONG. So and now the other thing is we need to find the lateral strain. So our lateral strain. Okay, it's very easy. So the deformation is just the 19.9837 divided and minus 20 millimeter divided by original 20 millimeter. Okay, so what's the value? What's the value of this? I think the value is very close. N minus 8.15 times 10 to the power minus 4. That's the strain on lateral direction. Okay, and so what's our Poisson ratio? Our Poisson ratio is just the ratio. You don't forget a minus sign. Okay, so lateral direction is minus 0.815 times 10 to the power minus 4. Longitudinal is 2.333 times 10 to the power minus 3. Okay, so we can cancel out this negative sign. So what's the value? Let's go. What's the value? So let's see what's the value would be. So 8.15 divided by 2.333 and divided by 10. So it's 0.349. Okay. So Poisson ratio is 0.349. Okay, so we have elastic modulus. So what's our shear modulus? I think we can have the answer right now. So, okay, our shear modulus is equal to, okay, 68.15 gigapart. Okay, and divided by 2 and 1 plus 0.349. So what's the value? Okay, let's see. Okay, so 1 plus 0.349 times 2 and the inverse times 68.15. Okay, so it's 25.26. Okay, so it's about 25.3. Okay, 25.3 gigapar. Okay, it's about 25.3 gigapar. Okay, so that's the elastic modulus and shear modulus based on the proper description. Yeah, it's not difficult calculation. You just need to know. You just use the Poisson ratio to find using the elastic modulus and use the Poisson ratio to calculate shear modulus. That's it. Yeah, yeah. My PowerPoint, the answer here is not exactly correct. So I missed the shear modulus. Okay, so let me add this. Yeah, it's so annoying. G equal to 25.3 gigapar. Okay, so I just start the video here. See you in another video. Okay, bye bye. Okay, bye 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 bye. Oh, okay.